Watch a freight train long enough and something starts to look strange. Almost none of the cars look alike. One is a sealed steel box. The next is open to the sky. Another drops low between its wheels, while farther back sits a rounded tank. Then comes something so long and complicated that it barely looks like a railcar at all. So why does one train need so many completely different kinds of cars? At first, a simpler answer seems possible. Build one strong platform, put the cargo on top, and secure it. But freight does not behave that neatly. Some loads need shelter. Others create problems because they are round, tall, liquid, or incredibly heavy. The shape of a rail car is usually a clue to the problem its cargo creates, and the easiest place to see that logic is with the most ordinary freight car of all. Let's get into it right here on Small Things. Why a boxcar is a box. A boxcar looks almost too simple to explain. It is basically a steel room on wheels, solid sides, a roof, and large sliding doors. That plain shape works because much of freight has a simple requirement: keep it protected and easy to load. Packaged goods and paper products do not need a special cradle or unloading system. Open the side door, move the load in by hand or forklift, close it again, and the car becomes a moving warehouse. Change the cargo, though, and the box changes too. Products that must stay cold can travel in refrigerated boxcars, where insulation and refrigeration equipment turn the car into a giant cold room. Lightweight but bulky freight creates another problem: volume. High-cube boxcars simply add height, but that space only helps if the car still fits beneath bridges and through tunnels. The railroad eventually sets the limit. The boxcar works because it solves protection and access with one simple shape. Some loads, however, do not need a roof at all. They need an easy way out. Why some cars are open and why their bottoms matter. A gondola can look like someone took a boxcar, removed the roof, and stopped there. For certain loads, that is almost exactly what you want. Scrap metal, ore, coal, sand, and other bulk materials can be dropped straight in from above. The high sides keep them contained, and a little rain may not matter much. The real difference appears when it is time to unload. A gondola may be emptied with a crane or other machinery. At some bulk terminals, a rotary dumper grips the car and turns it far enough for the contents to fall out. A hopper car takes a different approach. Look underneath one, and the floor is no longer flat. The body narrows into sloped sections leading toward discharge gates at the bottom. Open those gates and gravity does most of the work. Covered hoppers keep the same idea, but add a roof for material that must stay dry, such as grain or sugar. A gondola mainly needs to hold bulk material securely. A hopper is shaped so that material can leave through the bottom. The cars may look related, but the unloading method changes the geometry. Now swap loose material for something solid, heavy, and round. That creates a very different problem. Why steel coils? Get their own car. A steel coil looks harmless enough from a distance, just a giant roll of metal. On a moving train, its shape becomes the challenge. A large coil can weigh many tons, concentrates that weight into a small area, and has one especially inconvenient feature: it can roll. That is why coil cars do not simply present a flat deck and hope the restraints do the rest. Their bodies use troughs or cradles that support the coil and help hold it in position. The car itself becomes part of the restraint system instead of leaving everything to chains or straps. Many coil cars also have removable hoods. Those covers may look like something that holds the coil down, but their main purpose is usually protection from weather and contamination. The cargo may not be delicate at all. The problem is its geometry. A round object weighing many tons needs a car designed around the fact that it wants to move. Once the challenge becomes height rather than rolling, the railroad has to think about everything above the train too. Why containers? Sit down inside the train. Shipping containers changed freight by standardizing the box itself. The same steel container can move from ship to train to truck without anyone opening it and transferring the goods inside. That reduces handling and makes different transportation systems work together more easily. On rail, containers can also be stacked too high. That creates one obvious problem: height. Place 2 containers on a conventional flat car, and the top of the load rises much farther above the rails. Suddenly, bridges, tunnels, signals, and other overhead structures along the route matter just as much as the car itself. A well car gets around part of that problem by lowering the first container into a recessed section between the wheel assemblies. The lower box sits closer to the rails, so the entire double stack rides lower than it would on a flat deck. It is clever, but not universal. Some routes have still needed tunnels enlarged, tracks lowered, or bridges modified before double-stack trains could fit. The strange dip in the middle is not wasted space. It is how the train steals back a little vertical room. There is even a spotting clue here. When a double-stack train seems to ride surprisingly low, look at the car underneath. The well is doing much of the work. Solid cargo creates one set of problems. Liquids change the rules again. Why tank cars are round? Look at a tank car from the end and one feature stands out immediately. There are no square corners. That makes sense once the cargo stops behaving like a solid object. Liquids flow into every available space, while gases may need to be carried under pressure. Both call for something built more like a vessel than a box. The cylindrical body is especially useful for pressurized service because curved walls handle internal pressure more efficiently than large, flat panels. But the familiar round shape does not mean every tank car is built the same way. Non-pressurized cars can carry liquids that do not need substantial pressure. Depending on the cargo and design, unloading may happen through fittings or a bottom outlet that lets gravity help. Pressurized cars have tougher requirements. Their shells must handle higher internal loads, and valves or other fittings on top may sit inside protective housings. Cars carrying certain hazardous materials can also include head shields at the ends to reduce the chance of the tank being damaged in a collision. So a tank car is not simply a round box for liquids. Its details depend on what is inside and what that material can do. Then you meet a load so large that putting it on a normal car stops working altogether. The railcar, where the cargo becomes part of the car. Most freight goes inside a car, on top of one, or inside a tank. Some loads are too large even for that. Massive power transformers, reactor components, and other industrial equipment can weigh hundreds of tons. Put that weight on a conventional flat car, and too much force would be concentrated onto too few axles. A Schnabel car solves the problem in a way that barely resembles ordinary freight transport. The car is built in 2 large sections, one on each side of the load. Heavy arms reach inward and attach to the cargo, suspending it between them. In some configurations, the load effectively becomes part of the structure connecting the 2 halves. That is also why these cars can have so many wheels. More axles spread the weight across a longer section of track, so no single wheel set has to carry as much. Some Schnabel cars can even shift the suspended load slightly sideways or vertically. On a carefully planned route, that movement can help squeeze an enormous object past platforms, structures, or other tight clearances. By this point, the car has almost disappeared as a separate object. The railroad is not simply putting cargo on a car anymore. It is building the car around the cargo, and freight is not the only reason strange machines end up on the rails. The strangest cars may not carry cargo at all. Some of the oddest vehicles on a railroad are there to repair or inspect the track beneath them. A ballast tamper vibrates and packs the crushed stone under the sleepers, helping restore track support and alignment. A rail grinder deals with the steel itself. Wheels gradually wear the rail's surface, so grinding machines reshape it and remove irregularities before they become more serious. Then there are track geometry cars. Instead of carrying freight, they carry measuring equipment that checks gauge, alignment, curvature, and other details that are difficult to judge accurately by eye. These vehicles follow a different rule. They are not shaped around a commodity. They are shaped around a job. Not every unusual rail vehicle is delivering a load. Some are there because the railroad itself needs maintenance, measurement, or repair. Once you start looking at trains this way, the shapes become much easier to read. The next time a freight train passes, do not start by asking what every car is called. Ask what problem its shape is solving. A low floor may be stealing clearance. A sloped bottom may be turning gravity into an unloading system. A cradle may simply be keeping something round from moving. A tank may be dealing with pressure rather than just holding liquid. Once you notice those clues, the strange shapes stop feeling random. The names matter, but the shapes often tell the story first. A freight train is not really a collection of different-looking cars. It is a line of different engineering problems, each given wheels. That is why one train can look like dozens of completely different machines joined together. What is the strangest railcar you have ever spotted? Tell us below, and subscribe to Simple Thing for more stories hidden inside things we pass every day.